Hello and welcome. In this lecture, I'm going to talk about equilibrium of a rigid body, and we're going to learn how to draw free body diagram for a rigid body. Before we start, I want to kind of remind you what is the difference between a particle and rigid body. Particle and equilibrium of a particle is something that we've dealt with before. If you remember, particle is something that has a mass, but it has a size that can be neglected. We draw particle like a point, particle A. We draw the free body diagram for particle A. We put all the forces that are applied at that particle, such as F1, F2, F3 here, and they are what we call concurrent forces. That means they all go through the same point. And if you remember, equations of equilibrium for a particle was summation of all forces. They should be equal to 0. This is a vector form, just remember. That means summation of forces in x direction, summation of forces in y direction, and summation of forces in z direction. They need to be 0. Since the forces are concurrent, means they all go through the same point, applying principle of moment here doesn't really mean anything because they all go through the same point. So now let's look at the rigid body. Rigid body, on the other hand, rigid body, you cannot ignore the size anymore. Rigid body is considered a combination of large number of particles. So someone might say, well, why don't they just call it a body, another rigid body? Well, the reason is it is assumed that all particles, they all remain at a fixed distance from each other, both before and after the load is applied. In other words, the rigid body does not deform or change shape or form. So for a rigid body to be in equilibrium, we're talking about equilibrium, net forces applied to that rigid body, as well as net moment about a certain about an arbitrary point, let's just call it O, must be 0. So let me write it in equation form. Summation of forces equals 0. Summation of moment about an arbitrary point O needs to be 0. There is an and between these two equations, and this is what we call necessary and sufficient conditions for equilibrium. Okay, so this rigid body that I have, which I want you to remember, this is a 3D rigid body. It's a potato, right? It's subject to some forces, F1 through F4, and two couples moment. And how do I know these are moment? By looking at these little arrows that they put, which shows the direction of rotation. And if you use right hand rule, the head of the arrow shows the direction of moment. So for this potato to be in equilibrium, it needs to have summation of all forces equal to 0, summation of moment about any arbitrary point be equal to 0 for equilibrium. Let's look at the procedure and how we approach these problems to solve equations of equilibrium for these problems. So same as before, step 1 is to draw a free body diagram, or as we like to call it, FBD. So if you remember, free body diagram had three steps in itself. Step 1, let's call it 1-1, was to isolate, okay, that means remove all constraints, supports, ropes, anything, and just isolate. And here we emphasize a little bit more. Draw outline of the rigid body. Before we had a particle, so it was just a dot. But now we're going to draw the outline of the rigid body. Step 2, oh, it's 1.2. It's put all active forces on there. Some people like to call it external forces. Basically, anything that is trying to mess up our equilibrium. Step 3 is to put all reactive forces. Well, active forces are trying to mess up the equilibrium. Reactive forces are trying to keep the equilibrium. Why is this word so hard? Equilibrium. They're trying to stop those active forces. For rigid body, we are going to learn different ways that supports, constraints are working to keep a body from moving. Okay, so that's our rigid body, or sorry, free body diagram, which we're going to do some practice on. Step 2 is applying the equations of equilibrium. Equations of equilibrium, meaning summation of forces equals 0 and summation of moments about point A equals 0. So if you remember that potato that we had from before, from previous chapters, we learned that all of those forces, I can take them all and put them at a point, any point, and just find a resultant force. So this summation of forces that I have is basically my resultant force that I've learned how to find it from before. Also, all of those couples moment, and if I'm moving some forces to point O, are going to generate some moments. Sorry, this is going to be MR, resultant moment at point O for me, which is this guy right here. So these are my two equations that I need to satisfy. So step 1 is to draw free body diagram. Step 2 is to satisfy these two equations. So the meaning of these, one more time, is no translation, no movement. The meaning of the second equation is no rotation. Remember, there is an and between these two. They need to be satisfied at the same time. All right, so now I'm going to go back and kind of start working on this step 3 of a free body diagram, and learn how to draw a free body diagram, then how to apply the forces. So we got to learn different types of supports that are used in problems of this chapter and similar chapters that they talk about rigid body. So I'm going to go through some of the common ones. So the first one that I'm going to talk about is what we like to call it a roller, but it's also similar to a rocker. Here, the first picture, I have an example from a bridge that is on a rocker. The reason that they use rockers on bridge girder is to allow for thermal expansion, and let the bridge move a little bit to the left and to the right, or provide some wiggle room. Or the figure that I have below it is a beam put on a roller. So think of this roller as a pipe, and you're putting your beam on a pipe, and it is able to move to the left or to the right, but it cannot go this way. It's preventing. So whenever you want to draw a free body diagram and you want to find reactive forces, so you have to think about which way the support is not moving. That's what we care about, because whichever the support is preventing movement, that's where it is going to create the reactive forces for us. So what I like to do, and this is only my method, is I like to draw a little table for myself. I'm going to draw a little table. So this is a 2D problem, so there's only x and y. So my x-axis, my y-axis, I like to write x, y, and I like to write moment. So now we're going to look at the roller. If I put my beam on this roller, or any of the figures that you see here, any of these three, can my beam, can the beam move in x direction, to the left or to the right? If this beam is kind of resting on a pipe type of thing, yes, it can move to the left or to the right. So I put yes. Can this roller move any of these figures down here? If I want to number them 1, 2, 3, any of them move up and down. So 2 of them can move up, but none of them can move down, and the middle one cannot move up or down. So I'm just going to write no, because there is a restriction on y-axis movement. Now let's look at the moment. Can any of these beams freely rotate? Is it possible for them to rotate? Yes. Can this beam in the figure with the 2 star rotate? Yes, it's able to rotate around that point, whatever we want to call it. So we write yes. We care about what? Which way it is not moving. So we are going to put a force in y direction. This is what we care about. What does that mean? So that means step 1 is draw outline of your shape. Step 2 is put active forces, which in this case I don't see any, but let's say there was an active force of whatever, 100 newtons here. Step 2 is put the active force of 100 newtons there. Step 3 is to put reactive forces, and what we care about is the no in our table. In the direction of y, point A cannot move, so I'm just going to put an AY as my free body diagram. So wherever you see a roller, any of these shapes, or a rocker, there is a y reaction force at that point. Let's look at another common one. So this one is what we call a pin. So usually on the other side of the bridge, the other opposite to the rocker, there is also a pin. So one side is fixed, the other side can move left and right. So this picture is an element on a bridge. The second picture is I think a hydraulic arm connection on a tractor, and that's connected through a pin. So this is a pin right there, and then this lower element is these two that is holding it, and this one right there is the member. So that means the member can go up and down, it can go this way or back, but it cannot move in any other direction. So let's see, I'm going to put another active force here because this beam is cut off. We don't know what happens there. So let's put 50 pounds there. So now I want to draw a free body diagram. Step 1, outline of my shape, isolate, remove the support, put active forces on there, forces or external forces that are trying to mess up the equilibrium, and then I have a reactive force at point B. I'm going to form my little table here again. I'm going to write pin, I'm going to write X, Y, moment. Going to draw my little axis here, X and Y. So let's see, this pin is fixed. So can it move to the left or right? To the right or left? No, it cannot. So in X direction, it cannot move. All right. Again, it's fixed. It's bolted to the ground. Can it go up or down? No, it cannot go up or down. It's fixed. So there's restriction in Y direction. Can this arm rotate? Can this beam rotate? Yes, that's the whole point of a beam. So it can rotate. So I put yes. What do I care about? I only care about the nose in my table. I have a no in X direction. I have a no in Y direction. Point B, where's point B? Right there. So I'm going to put a BY, and I'm going to put a BX. I just put them in positive direction. Some of you might be wondering which way I put it, or how did I know it's pointing up, pointing to the right. At this point, it does not matter. At this point, I just like to put them in positive, my positive axis. But when we get to the examples, I'm going to explain it does not matter which way you put the unknown reaction forces if you cannot figure them out which way they're pointing. So we're going to talk about that. So don't worry about the direction yet. All right, let's look at another common support, and that's a fixed support. Here I have an example from floor beams that they're welded. They are welded here, and they are absolutely 100% fixed. Okay, so let me put another active force here of 25 pounds. And I want to draw a free body diagram. Step 1, isolate an outline of my beam, remove the support, meaning remove that wall. Then put the active force, the forces that are trying to mess up the equilibrium on there. And now for reactive forces, I'm going to make my little table again, fixed support. I'm going to make X, Y, and moment. All right, let's see. It's a fixed support. So guess what? It's not moving in X. It's not moving to the left or right. So restriction in X direction. Nope, it doesn't move. Can it move up and down? Same way. Nope, it doesn't move up and down. That's the whole point of having a fixed support. Can it rotate anyway? Nope, this cannot rotate anywhere. Anyway, either positive or negative. Nope, that's the whole point of it. What do I care about? I care about the nose only. Every time I see a no, I'm going to put a force or a moment in that direction. In X direction, the answer is no. I'm going to put and whatever. Let's call this point F. We usually use F for forces, but this is a fixed support, so let's put F there. So I'm going to say there's an Fx. Then I go to Y. Is there Y? Nope. I'm going to put a Fy there. Is there a moment? Nope. I'm going to put a moment there. So now I have two forces in a moment as a result of a fixed support. So that's my free body diagram. Here's another one. This is called a smooth surface or frictionless surface. Here are examples. You can see the ends of those beams, or there's a concrete girder that also rests on a ledge. So I want to draw a free body diagram for this one. Well, let's assume that there is a weight here, W of this beam. So to draw the free body diagram, step 1, isolate, remove the support, which is that surface that's resting on. Step 2, active forces. I'm going to put a W, and I'm going to make my little table here, X, Y, Z. So let's see, my X, my Y. Can this one move in X direction? Can it slide left or right? Yes, I don't see why not. Nothing is preventing it, so it's a yes. Can it move up? Yes, it can. Can it move down? Nope. So doesn't matter. If one of them is restricted, there is a restriction in Y. Oh, why did I put Z? It should be a moment. Can it rotate? I don't see why not. It can freely rotate to the left, to the right, so it's a yes. What I care about, I only put a force in the direction of restriction. So let's call it surface Y force. So this is what I have for free body diagram of a contact surface or frictionless surface. The thing that you got to know, this force is always perpendicular to the surface, always perpendicular to the surface. I have some examples for you guys that we're going to look. So if you look in your textbook, in two-dimensional, there are different types of support and different types of restriction on movement, and they listed the suggested free body diagram for them. So restriction in Y, there's a free body diagram. Restriction in this way, no moment, free body diagram. A collar on a slider, or a pin on a groove, or a slot, you can see which way it's restricted movement. It can move this way freely, but it cannot go this way. Also, it can rotate. So this is a yes, this is a yes, this is a no, and that's where you see the force, and so on. So you can go through these tables through any of the textbooks that you have. They have the name, they have an explanation for them, and their free body diagram. So here, let's look at some more examples, a little bit more complicated. So this is a pedal. The person is pushing. A, B, forces applied, blah, blah. So let's look at the system a little bit close up. So this one is what it looks like. The person is applying force F. There's a spring, there's a rod, and we want to draw a free body diagram of a rigid body. We cannot assume this is a particle because now the size and where the forces are applied, they matter. They're applied at different distances, so we cannot move them and put them at one point and assume it's a particle. The first thing I do, I only drawing free body diagram. I'm not solving for anything. Step 1 of the free body diagram, which is one of the most important steps, is to isolate what I'm trying to draw. You have to decide right there and right then what you're trying to draw. I'm trying to draw a free body diagram of, this is what I'm shading. Okay, so let's call member member OAB. All right, so now that I have that, I'm going to isolate member OAB. I'm going to draw the outline of it. Doesn't have to be perfect. It's not art, it's engineering, so we should be fine with just something that represents the outline. Okay, step 2. So that was a step 1. Step 2 was put the active forces, external forces, which here I have force F. Okay. Step 3, put the reactive forces, the forces that are trying to keep this from being messed up or keeping it in equilibrium. I have point B, which I can put let's call it Bx. It's in the direction of that rod B. I have a spring applied at point unknown. I like to call it point C, so I can call this Cx. And then I have a support at this point. So you got to think, what does this look like to you? This to me looks like a pin. So point A is a pin. I'm going to draw my little table quick. X, Y moment. I'm going to X and Y and see which way it is moving, which way it is not moving. So in X direction, does it move X left or right? Nope. So I'm going to put a no. In Y direction, does it go up or down? Nope. So I'm going to put a no. And can it rotate about point A? Can it go clockwise, counterclockwise? Yes, that's the whole point of having a pedal, because it can rotate. So it's a yes. I don't care about yeses. I care about no. Whichever you see a no, put a force there. So I'm seeing an X. I'm going to put an AX. I see a no in Y. I'm going to put an AY. And this is my free body diagram for this pedal. Again, I'm not solving it. If I know the amount of F, I can apply equations and solve it. But right now, I'm only focusing on drawing the free body diagram. Here's another. So I was going to draw that free body diagram for you, but it appears that it's already there. So let me see. So this is two huge pipes are being carried around. So the idealized situation is just basically two circles resting on a on a surface, which we call it a smooth surface. So let me draw, although it's there, but let me draw it again. So it is free body diagram of A and B. So we're trying to draw FBD of A and B, which I usually don't like to do that. I like to have separate free body diagrams for each of my free body diagram, but that's okay. So I have A, sorry, the circles are terrible, and B. Put active forces, which I'm assuming somewhere in that problem it tells us that, hey, this one has weight of 1, this one has weight of 2. Seems that we have the weight. We usually put the weight at center of gravity, which for them is going to be in the center, although you don't see anything in there, but the weight is still applied at the center of gravity. So now I have the smooth surface. Let me quickly go back here. Similar to this one. And remember, I said the forces are always perpendicular to the surface. So let me go back here. There we go. So I have one surface here, one surface here. I have one contact here, my reactive forces. Call it T, so I'm going to call it T1. I have another point of contact here, again perpendicular to that surface. So call it F, I'm going to call it F2. And I have another point of contact there. I'm going to put my next force of P over there. Each of these are 90 degrees perpendicular to that surface that are in contact with. Okay. Let's look at another one. So a loader or to the right. The idealized situation is a skid loader. It is carrying some load of 900 pounds in its bucket. We are trying to draw a free body diagram. So let's see. Free body diagram of the whole thing. So step 1, isolate, remove the support, which is the ground. So remove this. And again, it's not art, so it doesn't have to be perfect. I'm just going to draw something like this, very generic. And I'm going to have 900 pounds. That is the external force. I have another one, which I don't know how much it is. Well, let's call it W1. It's from that point G. So these are my two external forces. And I have 2 points of contact. And it's like a frictionless or a smooth contact surface. So I'm going to have 2 forces, AY and AB. Sorry, BY. There is no X and Y. Why? Because if you look at that little table, X, Y, M, can this move left and right in X direction? Yes. Yes. Can it move in Y direction? It probably can go up, but it never can come down. So there's a no. Can they rotate about point A? Yes. I mean, it's possible. So that's where I care about the Y direction, and they are perpendicular to the surface. Okay. Here's another one that I'm going to draw and find the draw the free body diagram for. So step 1 of free body diagram is isolate and draw outline of the shape. I'm going to draw outline of this whole crane arm, whatever it is called, AB. Let's call it ABG. So free body diagram of ABG. I'm going to draw outline of it. Something like that. I didn't include any ropes, any weights, any supports. Now I'm going to put active forces or external forces on there. What I see is a weight of whatever that is, newtons. I think it's going to be 23, probably 50, or 2.3 kilonewton, or 23. And there's another 0. 23 kilonewtons. The other thing that I see here, there is a weight. I don't know how much, but when they show that center of gravity in G, that means there is a weight there too, W1. And I see 2 support reaction. Okay, look at point A and tell me what is point A. Looks like a pin to me. Look at point B. What is point B? That looks like a rocker. So I'm just going to write roller, point B. I'm going to make my table X, Y, and moment. So let's look at each of them. Let's look at point A. Excuse me. X and Y. It's a roller, point A. Sorry, it's a pin. Does it move in X direction? Does it go left or right? Nope. There's a no. Does it go up and down? No. Does it rotate about point A? Yes. So clockwise or counterclockwise? Yes. Point B, does it move in X or Y? Well, it probably can go to the right, but it can never go to the left. The wall will stop it. So any restriction in that? Oh, sorry. I have to say no. Doesn't move that way. Can it move up and down? Yes, there's nothing in y direction that prevents movement, so it's a yes. Can the whole thing rotate about point B? It's a yes. Here's another thing. When you look at the roller or pin, only look at the roller, because some people might think, well, sure, it can rotate, but something else is preventing it. You only look at each individual support, each individual at a time. You do not care what's happening anywhere else. Same thing with pin. When you look at the pin, you only look at the pin, and you do not care what is happening with the rest of the beam. So point B, point A, let's start with A. X is a no, Y is a no, moment is a yes. So I'm going to put AX and AY. I'm not going to put a moment there. Point B, only X, I see a no. So I'm going to put a BX in that direction. So this is my free body diagram. If I have the weight, I have 3 unknowns, and I can move on and solve this problem. So these were, whatever we practiced so far was 2D and X and Y direction. So we only had to deal with sigma X or Fx, Fy, and moment. But in real world, in reality, the supports are 3D. Again, if you look at the textbooks from your tables from your textbook, you're going to see different type of support. Some of them are similar, as we've seen before. Like, look at this one. That's just like the smooth surface that we saw in a 3D format. Okay, so the rules like before still applies. If a support prevents, okay, that's the key word, whichever it prevents, that's where we care about. Translation, meaning movement in X, Y, or Z. Okay, then a force is developed in that direction. Okay, force Fy, Fx, Fy, and Fz. If rotation is prevented, a couple moment is developed in that direction. So it could be Mx, My, and Mz. So there are different kinds of it. So journal bearing is a very typical one that used in 3D. A fixed support is another one. Ball and socket is another one. Fixed support, ball and socket. So you can go through the table on your own. Again, whichever the movement is prevented. So for example, for ball and socket, it's a fixed support, but it can rotate in all 3 directions. So there is no rotation prevented. So it does not generate any moment in any direction. But it's 100% fixed in X, Y, and Z. So it generates 3 forces in X, Y, and Z. So you got to go through them and kind of get familiar with each type of support. But as I mentioned, journal bearing, thrust bearing, ball and socket, and fixed supports are the most common one that you gotta know what forces they're applied and so on. So this is another ball and socket down here. This one is a thrust bearing. The difference between the thrust bearing and journal bearing is journal bearing can move in this direction and it can rotate in this direction. Thrust bearing, of course, it can rotate, but it cannot move back and forth. That's the difference between thrust bearing and journal bearing. So I have some examples for you. So this is a journal bearing. So journal bearing that we have. So let's see, free body diagram of this in a 3D space. Step 1, isolate. I like to draw a free body diagram of beam or rod AB. That means I'm going to isolate. Means remove everything else except AB. That's a step 1. Step 2, put active forces. The forces that are trying to move this. I have an F1. I see another one, F2. So these are the 2 external forces. Step 3, I don't see any weight. It doesn't explain to me. At this point, I'm not worried about it. Step 3 is to put reactive forces. That means the supports. So I see a tension going from point B to D, T1. I see another one going to point from B to point C. It's a rope, so it's always in tension. So it means it's going away from the point. And I have a journal bearing. So a journal bearing, I'm going to make my own table again. The difference is this one is X, Y, Z, MX, MY, MZ. Now I have 6 terms to look at. A journal bearing, I told you that it can move back and forth and it can rotate. Okay, so let's see. In X direction, does this move in this X direction? No. Does this move in Y direction, back and forth? Yes. That's the point of having a journal bearing. Does this move up and down in Z direction? No, it doesn't. Okay. So I'm done with those 3. Now let's see. Does this rotate about x-axis, meaning this rotation here? Does this rotate about x-axis? I don't think so. That bearing is fixed and this rod cannot rotate. So it's a no. Can this rotate around y-axis? Meaning this way. Can it rotate about y-axis? Yes, it can. Again, that's whole point of journal bearing. Important point. I don't want you to look at anywhere else on that rod because some people might think, well, those rope doesn't let it rotate. It doesn't matter. We only looking at journal bearing. Only looking at the bearing. Not anything else. We do not care what is happening at point B. What ropes are there? Is it welded to the wall? Is it fixed to the wall? Is there on a roller? Does not matter. We only are looking at journal bearing. That's it. Okay, yes, it can rotate around axis Y. Can it rotate about Z axis? Nope, it doesn't. So what we care about is only the nose. These are forces, these are moments. So let me see. At point A, I have a x fx. Again, at this point, it doesn't matter, but I kind of getting used to putting everything in positive direction. Ax. Does it move in Y? Yes. I don't care. Does it move in Z? No. I care about that. AZ. Okay. Now let's move on to moment. Does it move in about MX, about x-axis? No. That's what I care about. So I'm going to put an MX here. So I like to draw like that. Some people like to draw just the vector, write M on it. Some people like to draw just the rotation, which is all acceptable. MY, does it rotate? Yes, I don't care. MZ, does it rotate? No. So I need to draw an MZ. Again, I'm just drawing all of these in positive direction. Sorry, I drew that twice. So this is my free body diagram for this problem. If you look back at the journal bearing, that's where you see it. It has a moment about x, fx, moment about z, and fz, there's nothing in y direction, no moment, no force. And that's what we got here, and that's all we care about. I have another example for you guys. This is what we call a fixed support. 100% fixed. Fixed in all directions. Does not move at all. Okay? So free body diagram of, this is important, A, B. I like to call that endpoint B. So let me draw outline of my rigid body. Remove everything that I don't need, any support, any constraint. Step 2, put active forces. I see one force of 150 newtons here. I see another force of 200 newtons there. I don't see anything else. Step 3, reactive forces. A fixed support. I'm going to do this a little bit quicker. X, Y, Z, MX, MY, MZ. I just told you that this does not move in any direction. It's 100% fixed in all directions. Does it move in X? Nope. Does it move in Y? Nope. Move in Z? Nope. Rotation about X-axis? I hope not. It's fixed. Rotation about Y? Nope. Rotation about Z? No. So we have 6 no's. We need to get to work and put 6 forces, 3 forces and 3 moments there. So let me see. Fx doesn't move. Ax. Y direction doesn't move. Z direction doesn't move. Rotation about X? Nope, doesn't happen. Mx. Rotation about Y? Nope, it does not happen. And rotation about Z, this way, right hand rule, it is not happening. So for a problem like this, we have 6 unknown, and in future lectures I'm going to get into examples on how to solve examples. So one last thing that I want to mention is what we use to call as properly aligned bearings and hinges. So usually when you see a problem like this, A, B, and C, the first one we're looking here, that they have 3 bearings in 3 different directions. Okay, in cases like this, I'm going to write it here. Forces developed by bearings or in bearings are sufficient. Or in this case, forces developed in hinges are sufficient, and they prevent shafts from rotating, you know, about each coordinate. And that's why there is no moment reactions created for these bearings. So as you can see, although there are, I'm assuming, journal bearings, but you don't see any moments. I want you to pay attention here. I had a journal bearing. You see that? It generates moments. But here, because it is properly aligned, it does not generate moments. So for the problems like this, it usually tells you that they're properly aligned, or you can see that the bearings are in three axes, X, Y, Z, in every direction, so they prevent no moment is generated in those bearings. So here's an example. Again, I wanted to draw this for you, but I forgot to remove it. So there we are. C, B, A, as you can see, one is in Y, one is in X, one is in Z. So this is what we call a properly aligned. The problems are even tells us that they're properly aligned. So when you want to draw a free body diagram for bearing A, there is no moment there, no moments on B, and no moments at point C. What happens if you put moments there by accident? Then you're going to have too many unknowns and more unknowns that you have equations, and that will difficult or impossible to solve the problem. This is all I had for you. Thank you for watching.